Hi there, folks. This is the Algebra 2 midterm review, and as always, I am the amazing Mr. Jansen. So away we go. If we take a look at the first one, it's asking us to find the equation of the line that is parallel to y equals 3x minus 1 and passes through the point 1, negative 2. Remember, whenever we're trying to find the equation of the line, we're looking for two things. We're looking for the slope, and we're looking for the y-intercept. For this one, since it says we're parallel to this line has a slope of 3, and remember, parallel lines, the slopes are the same. So that means our slope is also going to be 3. And I use a fresh y equals mx plus b. And I plug in what I know. I know that the slope is 3. The b value is the thing I'm looking for. I just need an x and a y, which is why they give me this ordered pair. So I plug the 1 in for x, I plug the negative 2 in for y, and I solve this for b. So I've got a negative 2 equals a 3 plus b. I subtract the 3 from each side, and I find out that b equals a negative 5. So now I have the two pieces I need, which means my equation is y equals 3x minus 5. I plug in the slope, plug in the y-intercept. Okay. Number 2 is very similar. I still want to find the slope and the y-intercept because I want to write the equation of a line. This time it tells me I'm perpendicular to y equals 1/2 x plus 4. Remember, perpendicular, the slope of this line is 1/2. And perpendicular lines, the slopes are opposite reciprocal. So instead of a positive 1/2, it's going to be a negative 2/1, which is just a negative 2. And now once again, I use a fresh y equals mx plus b, and I plug in what I know. I know that the slope is a negative 2. B is the thing I'm looking for. So once again, I need an x and a y value, which they give me. So I plug the negative 4 in for x. I plug the 3 in for y. So I've got 3 equals 8 plus b. I subtract the 8 from each side, and I find out the b equals, once again, it's a negative 5, which is just a coincidence, but now the equation is y equals a negative 2x minus 5. Okay, so again, find the slope, find the y-intercept, plug it in. Parallel lines, the slopes are the same. Perpendicular lines, the slopes are opposite reciprocals. For these, it says to match the equation with the number and type of solutions. And as mentioned in class, some of these may be used more than once. Others might not be used at all. But when we're doing this, when we want to talk about the number and type of solutions, we want to use the discriminant, which, remember, the discriminant is b squared minus 4ac. It's the part of our quadratic formula that's underneath the square root. So I'm going to do that for each of these. So for the first one, I'm going to do b squared, so a negative 2 squared minus 4 times a, which is 3, times c, which is a 6. And I would just simplify this. That's 4 minus, this is 4 times 3 is 12, times 6 is a 72. So that gives me a negative 68. Since the discriminant is a negative 68, I know that that's going to give me two complex solutions. Whenever the discriminant is negative, it means I'm going to have two complex solutions because the thing under the square root for my quadratic formula is negative. Okay, so that's two complex. In number 4, I do the same thing. I find the discriminant, so that's a negative 3 squared minus 4 times a, which is 1, times c, which is a negative 15. That's going to be a 9 plus 60, which gives me a 69. And since the discriminant is a positive number that's not a perfect square, it means it's going to be two irrational solutions, which is letter C. Okay, two irrational solutions is what happens when I have a positive that's not a perfect square. When I do the next one, 4 squared minus 4 times a, which is 1, times c, which is a negative 7. That's going to be 16 plus 28, which is 44. Once again, that's a positive that's not a perfect square. So that's two irrational solutions again. And then the last one, I do b squared minus 4ac. So 4 squared minus 4 times a, which is 1, times c, which is 4. Which gives me 16 minus 16, which is 0. When the discriminant equals 0, it means that I have one rational solution, which is letter A. And the only one that hasn't been used is the two rational solutions. Remember, two rational solutions, when the discriminant is a positive, that is a perfect square. That's when we have two rational solutions. So that's numbers like 4, 9, 16, 25, things like that. okay? For number 7, it asks me to find the vertex of the quadratic equation. To find the vertex, remember the x value of the vertex is opposite of b over 2a. So the opposite of b is a negative 4 over 2 times a, which is a 1. So that's negative 4 over 2, which is a negative 2. That's only half of my vertex. That's the x value for my vertex. To find the y value that goes with that x value, I have to plug the x value back into the equation. So I do negative 2 squared plus 4 times a negative 2 plus 4. That's going to be 4 minus 8 plus 4. So it looks like 4, let's say negative 4 plus 4, which is 0. So the x value is negative 2. The y value is a 0. So my vertex is negative 2, 0. And this is special because if we look back at number 6, that's the same equation as we had in number 6. And with number 6, that had one rational solution. Well, now I can see my one rational solution. Remember, when the vertex, okay, is on the x-axis, it means that that is our one solution. So then the solution and the vertex are the same thing. They're all part of the same answer, okay? So the vertex doubles as my solution, which is also my x-intercept, okay? And that's a special case when we're looking at something that has one rational solution. It's also the vertex. For number 8, it says we want to know if the relation is a function. Remember, for a relation to be a function, every x value has to have exactly one y value. In other words, we have to make sure all the x values are being faithful to their y values. And if we look at the first ordered pair and the last ordered pair, we see the negative 1 over here with a positive 1, but then we see the negative 1 over here with a positive 5. So the x value is not being faithful to its y value. It's over here with a different y value. So that means this one is not a function. That one x value has two different y values. So this one's not a function. And that's it. That's all there's to it. In number 9, we just want to evaluate this. So we're going to plug the values in. So y, which is a 6, plus x, which is a 5 squared, plus 5 times z, which is 7, times w, which is a 40. And I just have to follow order of operations. I'm going to start inside the parentheses, gives me an 11. Over here, I can go ahead and do this multiplication. Well, I'll leave it till the next step. Next step in order of operations is exponents, so I'm going to do the 121. After I've done the exponents, now I could do the multiplication. So that's 5 times 7, which is 35, times 40, which is 1,400. And now I can do the addition, which is the 1,521. And that's it. Okay, so follow order of operations. Plug in the values, parentheses, exponents, multiplication and division, addition and subtraction. For number 10, we just want to solve this, and since this is an absolute value equation, means I have to split it into two equations. I have to do 3x plus 6 equals a 12. In other words, what's inside the absolute value could equal a positive 12, or what's inside the absolute value could equal a negative 12, so I have to set it equal to the opposite of that. And now I solve each of these. For the first one, I subtract the 6 from each side, which gives me a 3x equals 6. Then I divide each side by the 3. So I get x equals 2. Over here, I subtract the 6 from each side. That gives me a 3x equals a negative 18. I divide each side by the 3. And I find out that x equals a negative 6. And these are my two answers. I can plug them both back in, and they work. So my two answers are x equals 2 and x equals a negative 6. For number 11, this is a system of equations, and there's two good ways to solve a system of equations, either substitution or elimination. Substitution is when we solve for one of the variables, but if we look at this one, it's set up nicely for elimination because all the variables are lined up. And if we look at the y values, I've got a negative 3 and a positive 3 for coefficients, which means all I have to do is add these two equations together, and it will eliminate one of the variables. So here, 3x plus 2x is a 5x. The y's cancel each other out. 9 plus 1 gives me a 10. And now I can solve the equation that's left for x. I divide each side by the 5, so I find out that x equals 2. But I'm not finished yet. I still have to find y. So I have to take one of the equations. I'm going to take the second one, and I'm going to plug this x value in, and I'll find out what y equals. So I've got 4 plus 3y equals 1. Let me take it off to the side. I'm going to subtract the 4 from each side. So I find out that 3y equals a negative 3. And now I'm going to divide each side by the 3 and find out that y equals a negative 1. And I can write this answer as an ordered pair. The x value is 2, the y value is negative 1, so it's the ordered pair 2, negative 1. Okay, it's just a nice way to write an x and a y value that go together. Okay? For number 12, when you're multiplying three things, you just multiply left to right. So I'm just going to do this one step at a time. The 10 times the 6 is a 60. When I multiply variables, I add the exponents, and keep in mind this is an x to the first here. So that means this is going to be an x to the third, y to the third. And now I can multiply that by the negative 7, x to the negative 15th, y to the 8th. So 60 times the negative 7 gives me a negative 420. Once again, I add the exponents. That's going to be x to the negative 12th, y to the 11th. And then the last thing I have to do here is I have to take care of negative exponents. Negative exponents we have to flip to the other side of the fraction bar. And the only thing that has a negative exponent here is the x, so I send this x to the 12th to the denominator, and I make it a positive exponent. And now that one's finished. Okay? In number 13, if we want to add or subtract radicals, we need to have like radical terms, which means they have to have the same radical symbol with the same radicand. And none of these do the way they're written, so I'm going to simplify each one. So I'm looking for perfect squares that divide evenly into each. So a perfect square that divides evenly into 12 is a 4. So it's 4 times 3. Perfect square that divides into 27 is a 9. It's 9 times 3. And a perfect square that divides evenly, let me try that one more time. Perfect square that divides evenly into a 50 is a 25. So that's 25 times 2. Let me separate this. And now I can start taking the square root. The square root of a 4 gives me a 2. I write it on the outside. It's a change number on the outside. The square root of a 9 is a 3. It's a change number on the outside. The other 3 is still trapped. And then here the square root of 25 is a 5. It's a change number on the outside. The 2 is still trapped. And now when I look, I have two values that have the exact same radical symbol with the same radicand, the same number underneath. And that's these first two. So I can combine these values, which gives me a 5 root 3. And then I can't do anything with the minus 5 root 2. So that's it. Okay, I combine the like radical terms. In number 14, I'm just simplifying this. So I'm looking for perfect squares once again. So for 32, I can break that into 16 times 2. X to the third I can break down into x squared times x. Y to the 8th is already a perfect square because the exponent's divisible by 2. And now I just start taking the square root of each. The square root of 16 gives me a 4. It's a change number on the outside. The square root of x squared is an x. And technically that's the absolute value of x, but we're going to assume all variables are positive. And the square root of y to the 8th is y to the 4th. And now the things that are still left under my square root are the 2 and the x. Okay? In number 15, the square root of 81 is easy enough to do. That's going to give me a 9. But when I take the square root of a negative, that gives me an imaginary number, which is I. So the square root of a negative gives me an I. The square root of 81 is a 9. So the square root of negative 81 is a 9i. And that's it. In number 16, I want to use my distributive property. So I'm going to distribute this. And when I multiply, just remember the stuff on the outside gets multiplied by the stuff on the outside, stuff on the inside by stuff on the inside. So this first one, I do the 3 times the 2, which gives me a 6. I do the 5 times the 6, which gives me a 30 underneath the radical symbol. And I do the same thing with the next one. 3 times 3 gives me the 9. 5 times 2 gives me a 10. And the last thing I would do is look to see if any of these simplify, but unfortunately none of them do, so I leave it just the way it is. In number 17, I have to remember that I to the first is I to the second is negative 1, I to the third is a negative I, and I to the fourth is 1. Remember that that pattern repeats. And so every fourth exponent is going to equal 1. So when I look at this, I want to find the closest exponent that's divisible by 4. And for this one, for 66, I could say I to the 68th. 68 is divisible by 4, which means we're right here in my pattern. So I to the 66th would be back 2, which puts us right here at negative 1. Okay?